Welcome, everyone. It's a great day for us. We're going to celebrate the Den Hartog lecture, and our speaker is Tom Hughes from the University of Texas in Austin. But before I get to introducing him to you formally, I want to take a
I don't think that's
few
working.
minutes
Yeah.
to tell you who Den Hartog was. So this is a picture of Den Hartog. So the National Academy of Engineering, when someone passes, they write this a memoriam, and this is a picture from his memoriam written by Steve Crandall. So Den Hartog, Jacob Peter Den Hartog, died in 1989. He was born in 1901. So he came to the U.S. when he was 23 or 24 years old. He's originally Dutch, and he found himself a job working with Timoshenko as his boss at Westinghouse Research Labs. And he did that for about 6 or 7 years. And when he came, he basically had a master's degree. And in the evenings, he would study at the University of Pittsburgh to get his PhD. And his boss was Timoshenko. And then from there, he came to Harvard, was there for about 10 years. Then the war happened, he signed up, and he joined the Navy, he got commissioned, he was a commander, a captain, he did well. And then meanwhile, MIT, whoever the head of the department was at that time, offered him a job that after he finished, he should come back and teach at MIT in our mechanical engineering department. So he did that for several years, for 22 years. He retired in 67. In between, he was department head for about 4 years. He's very highly decorated. One of the medals that he got was the Timoshenko Medal. And the department in 1981-82 established the Den Hartog Prize for Excellence in Teaching. That's not why we're here today. That's another Den Hartog Award. So the other one is the lecture for someone from outside, but the department also has a Den Hartog Prize. So in addition to all the papers that he wrote and the awards that he got, one of the legacies of Den Hartog are his books. He wrote several of them. These are the 4 prominent ones. And this one, Mechanical Vibrations, is probably his most famous book. It went into 4 editions, and I read some where it got translated into 14 different languages. And it served that book, and together with all these other books on mechanics, advanced strength of materials, served many generations, both at MIT and across the world. In fact, I remember having a copy of that back at IIT when I was an undergrad.
That's true.
Right? Okay. So there was mechanics in the 1920s, 30s, 50s, and then there's modern mechanics. And there's a big change, and the change is going to be celebrated today with Tom Hughes visiting us. And Tom Hughes, in those days, there were no computers. Computers came about in the late 60s, and we have the embodiment of modern mechanics and computational mechanics through Tom Hughes. So this is Tom Hughes. He'll stand up in a moment. Tom Hughes is currently at UT Austin. Previously, he was at Berkeley and Stanford and Caltech. And he has done many things in computational mechanics. He'll tell us some about the history of mechanics. His PhD was in 1973 from Berkeley, and he has many awards, NAE, NAS, Royal Society, the Timoshenko Medal, and many, many more. The list is very long. I didn't want to put up the whole list. And he's also been very instrumental in setting up societies for computational mechanics and editing the premier journals of computational mechanics. So the Computer Methods and Applied Mechanics. And how many years did you do this?
43.
43.
Okay.
And he rejected a couple of my papers.
Correction. I rejected all of his papers.
No. And there is famous to the point there are awards now named after, including the ASME Hughes Young Investigator Award, as well as the Computational Mechanics Award, in fluid mechanics is known as, goes by his name. So just like Den Hartog, Tom Hughes also has written many, many good books. And here are some of them. I didn't list all of them. I said some books. This is his classical finite element books. This is his classical book on plasticity with Juan Simo. This is with Marsden on mathematical populations. And then his most recent book on 2009 is this isogeometric analysis, which is one of the things he's going to talk about. With that, please welcome Tom Hughes.
Well, thank you, Lalit, for a very kind introduction. I might add that one of the other authors of isogeometric analysis is sitting in the audience here, Yuri Basilevs. Where did he go? Oh, there you are. Okay. Let me begin saying I was in the presence of Den Hartog once. I don't remember exactly when it was, but it was at a winter annual meeting of ASME. And that's what the annual meeting was called in the old days. And I happened to wander into a room where he was receiving an award. And he was giving some remarks. And what he said during his remarks were that he got all of these awards because he lived a very long time. And he was making other jokes. I remember thinking at that time, since I was younger, maybe there should be young awards. So I instituted a few of those, actually, in 3 different societies. And it was sort of inspired by those comments. Of course, now that I'm a little older, I'm thinking of instituting some over 90 awards and over 85 awards. It seems like a good idea all of a sudden. Okay, so title. I'm going to talk about the finite element method and isogeometric analysis and give a little overview of history with just a couple of points. I told the guy that taped me that my body rejects these things. So we'll try to keep that. All right. All right, so we'll start with when did the finite element method begin? That's the past. The present, it's an enormous success, undoubtedly, and that will lead me to isogeometric analysis. I'll give you a brief review because I assume most of the people here have some orientation towards analysis, but not perhaps the geometric side of analysis. So this will be sort of a little tutorial on technologies that are used there. And then the mathematics of IGA, that's a field in its own right. And there are 3 areas that are primary. I will focus on one that I think everybody in mechanical engineering certainly will have understanding of. And then I want to talk about modeling. And you'll see that IGA and modeling are sort of synonymous topics. So the 2 major paradigms, boundary fitted and immersed. Then speculate on the future. So in the past, the question I'd like to address is when did the finite element method begin? I think it began right here at MIT in 1940 with a PhD thesis, actually in civil engineering, by Alexander Renikoff. And when I first encountered this, as you'll see in a few moments, at a place called General Dynamics Electric Boat, which is not far away from here when I was working before I did my PhD. But what Renikoff did is he took the sort of the knowledge at the time in what was called matrix methods of structural mechanics, which was basically beams and frames. And what he did is take the intellectual leap and try to put those together in networks, lattices that represented continua. So that was a jump. And a lot of the early people in finite elements attributed the ideas to him to go from beams to continua. So as I said, I encountered these methods when I worked at General Dynamics in Groton. And the thing that really made things go there, of course, was computers. The finite element method's existence is based on computers. And it was more than just that you could do numerics. It was giving you a different idea about how to use computers. And what was nice about working at General Dynamics at the time, they had a big computer, UNIVAC 1108, which was a supercomputer in its day, with enormous drum storage, like a big oil drum. And they were doing calculations of over 10,000 degrees of freedom around 1965. And the only places in the world where things like this were being done were in aerospace firms and defense industry firms like General Dynamics. But what they were using was the Renikoff method. And one of the lures when I interviewed there was that the unisphere, sort of the symbol of the 1964 World's Fair in Queens, New York, this structure was actually analyzed by the Renikoff method analysis group. And in the bio of the architect of this, it's mentioned that engineering the immense structure involved solving hundreds of simultaneous equations facilitated by computers used to design atomic submarines. That was absolutely true. And they were very proud of that fact. They did it as a consulting job. It's still standing and it looks just like this today. This is a more current picture. So this was really a beginning, but I think most people would attribute, at least from the mathematical point of view, to the beginning to a paper by Richard Courant. And it was published in 1943. It was based on an address given at an American Math Society conference in 1941. And then the paper was received by the editors about a year later, 1942. And the paper then was published in 1943. It was called Variational Methods for the Solution of Problems of Equilibrium and Vibrations. And in the paper, there was an appendix. And this appendix did not appear in the original address. It was specifically pointed out. It was called The Numerical Treatment of the Plane Torsion Problem for Multi-Connected Domains. And here are some cross-sections, and they are being discretized by the linear triangle of finite element analysis. And even in this paper, the word elements was used. Courant said, and I quote, "Of course, one must not expect good results, good local results from a method using so few elements." This didn't start the finite element method with a great bang. Nobody paid a bit of attention to this paper until the mathematical theory of the finite element method came along about a decade, 3 decades later, and then people rediscovered this paper. But this paper was known to people in another community, optimization, because it introduced the penalty function method. And they kind of picked it up, but its finite element history was obscured until that rediscovery. In engineering, usually people attribute the beginning to John Argyris, who was at Imperial College and had an institute in Stuttgart, Germany. And he wrote a series of articles in a now defunct journal called Aircraft Engineering. He was an aircraft structural engineer. And at the very end of that article, these were sort of matrix methods of structural analysis type papers. At the end of that article was a Wagner panel, essentially a shear panel, a 4-node quadrilateral. In addition to that pioneering contribution, which was around 1954, 55, 56, he gave a lecture to the Royal Society in England, the Royal Aeronautical Society. And he said, don't think of the computer as an arithmetic machine. Think it as an amplifier of human intelligence. And the title of it was The Computer Shapes the Theory. And I think today this is even more applicable than it was then, because you can see how what computation has done through AI and how it's completely changing how we think about things. So that was perhaps the beginning. There was another paper in 1956. A lot of people point to this paper as the origin of the finite element method in engineering. And this was a paper that was done by the Boeing research group, but that included two visitors who used to come in the summers. One was Ray Clough from Berkeley, a civil engineer, and Harold Martin from the University of Washington. And it was run by Jonathan Turner, who is kind of a luminary in his own right. And they were doing research on the stiffness method, as they called it. And in this paper, the linear triangle also appears. Now, if you go back and you search for finite element papers during these years, you will not find any in the citation indices. And the reason is the words finite elements were never introduced until 1960 in a conference paper by Ray Clough. So he has the honor of having named the method that stuck. And that didn't really catch on for about another 3 years. Then you start to see papers appearing in 1963 in the engineering literature. So it started primarily in aerospace engineering. They had the computers. It went to civil engineering in the 1960s, mostly through the efforts of Ray Clough, who also induced Oleg Zienkiewicz, another civil engineer, to get involved, who became the Pied Piper of finite elements, I would say. The mathematical theory began in the late 1960s, but in the 1970s and thereafter, the major area of finite element development was mechanical engineering, and that really began the era of computational mechanics and a focus on nonlinear problems, nonlinear mechanics problems. During this time, commercial code development began. The famous codes, Nastran, Mark, Abacus, LS-DYNA, were all initiated. In the 1980s, there was significant development in computational fluid dynamics. And with the realization that the methodology was not tied only to structures, people started to apply the methods to all sorts of problems, engineering, science, mathematics. Then, one of the biggest events, I would say, was the 1990s. And the repercussions of that are being felt today. And that is the widespread utilization of medical imaging, CTs, MRIs. So this provided the basis for patient-specific anatomic modeling. It's a window on human anatomy and physiology. And once you have an image, you can build a model. And once you can build a model, you can put physics on it and chemistry and mechanics, and you can solve problems. And that was the beginning of the era of computational medicine, and it's roaring along today. So the present. Nowadays, cars are designed in computers with the finite element method. They used to be crash designed. This is the first car that was crashed analytically, finite element model in 1980s. It was 1987. It was about 1985. But it was on the cover of the first edition of my finite element book. That was a Suzuki, and that was done by what was called Dyna 3D. Now it's called LS-DYNA. It's part of ANSYS. That's the major crash code in the world. And within 20 years, you had all sorts of different types of analyses of crash that were designing computers, designing cars. You had airbags that were deployed, anthropomorphic dummies, seat belts actuated, and it's even more sophisticated today. To give you an idea, the industry standard for the size of elements in these models is about 2 millimeters. So you can imagine how many elements are used in these automobile models today. Airplanes are designed in computers. I should say this was done with an element that we developed for that code way back when, earlier. And subsequently, as I said, in the 1980s, 1990s, fluid mechanics really began to blossom within the finite element method. This is a picture of a Falcon jet, and it's a high lift configuration, so it's a turbulent flow, full flow of around the airplane, as you can see. This was also done with some codes that were developed at Stanford and my group at the time, and that were taken back to Dassault and industrialized there. Dassault is a small aviation company. There's a Dassault System, which is a big CAD company, much bigger than Dassault Aviation now. It was a spin-off from Dassault Aviation long ago. But in any event, they do about 10,000 of these calculations a year, full 3D turbulent flow calculations, and many other types of calculations. So there's fluids, there's solids. Fluid structure interaction is an area that the finite element method owns, I would say. It's very easy and a variational way to do multi-physics type applications, and fluid structure interaction is one. This is a full body model, as you can see. It was done by a student in our group at Stanford at the time, Alberto Figueroa. And as you can see, the vessels are moving. They almost look like they're one-dimensional here, but this is about 100 vessels. It's fully three-dimensional analysis, including wall modeling with tissue-varying material properties. This gives you the idea of the resolution in the models, and these are just sort of standard calculations nowadays. So finite element method is an enormous success, but what are the underlying reasons? It's simple and it's general. The ingredients are basically two: function spaces, basis functions, and variational method. There are obviously, there's a lot more to it when you get down to more challenging problems, but that's the basis. You also have the concept of general purpose computer programs. These are applicable to all sorts of different applications, engineering, science, medicine. And that concept really didn't exist before. When I first got started, people were writing codes for an individual mesh for a problem. The mesh was wired into the code. Now you have these programs like LS-DYNA and Abacus, and you can apply them to all sorts of things. And a firm mathematical basis. So you have all of these things together. But the problems that remain are primarily in model creation. There's a bottleneck. It's a bigger problem to create models than it is to solve the PDEs on the models. You have geometry errors that are inherent in computer-aided design descriptions that have to be fixed before building a finite element model. You have to sometimes remove features which can be detrimental to accuracy. You've just got to clean up the geometry. It's a very trying task. Another problem is the promise of higher order elements that you would read about in the literature of finite elements, in the academic literature, has not really been realized in industry. There's a falling back on the lowest order elements typically in commercial and industrial applications. And closing the loop with design optimization. Design is embedded in CAD. The finite element method takes CAD. It leaves that data representation behind. It has a mesh. These things are no longer connected. They should be one, in my opinion. So this is a study that was done in Sandia many years ago, and it was an anatomy of where the time was going in the overall analysis procedure. And so it starts with CAD descriptions and then builds finite element models. And it was observed that more than 80% of overall analysis time was devoted to fixing the CAD geometry and creating the finite element models, the meshes. And it was a major bottleneck. And you hear this all over the place to this day. And very often, the finite element model is only an approximate geometry for several reasons. One is feature removal from CAD, and the other is the faceted approximation to smooth curve geometry. So why is it so time-consuming? This is a simple model of a B-pillar for a Honda, as you can see. This shouldn't take very much time, you'd think, to work with. The car is another matter, but one piece is nothing. So these are graphics. If you look closely, you'll find some other things going on. If you look at the data structures, you might be shocked to find it looks like something like this. These are untrimmed images of patches. Patches are rectangular domains, and trimming means you strip off the part that isn't to go into the physical geometry, and you map it into the physical geometry. So this little guy here consists of 1,280 trimmed surfaces, patches. They're not watertight and they are not connected. So you cannot bring them to life. They're dead. If you move one, it doesn't change anything else in the model. So the way I like to think of trimmed patches is that each patch is a phase field. And you have a phase of 1 where there's a material, and a phase of 0 where there's no material. So it's a binary phase field. That becomes useful when you want to bring things like this to life later on. So modeling is an enormous challenge. Fidelity is getting more demanding as time goes on. When you build models of things like this, you will model the individual bolts and nuts and everything. And occasionally you'll do an analysis, you'll find that the failure mode may be due to a fracture of a bolt. So if you eliminate these things to simplify modeling, you just don't get the right answer. So this is what we're chasing these days. So the objectives that we set some time ago was to reconstitute finite element analysis utilizing precise CAD geometry, possibly simplify model development thereby, and also to integrate design and analysis. And that's what led to the concept of isogeometric analysis. So the first paper that we published was in 2005, and the book is mentioned by Lalit in 2009. And there's been at least a mini boom in this topic. There are 6,300 papers according to Web of Science, and over 186,000 citations now to those papers. So what it is, it's based on the technologies that come from computational geometry. NURBS, T-splines, U-splines, the whole zoo of splines. It includes all sorts of design areas that are used in all sorts of design areas. Architecture, engineering, fashion, furniture, animation, graphic art, and visualization. So there are a lot of functions here. And it includes standard finite element analysis as a special case, but offers all these other possibilities. Precise and efficient geometric modeling, you might say exact geometrical modeling. Simplified mesh refinement schemes, I'll show you some of that. And one of the areas that's becoming more and more important in analysis is that in this technology, you have smooth basis functions with compact support. And you don't carry derivative or degrees of freedom of that nature, just ordinary primary value degrees of freedom. And what we didn't realize we were going to get, but we also got superior approximation properties. I'll show a little bit on that. And the potential of all of this then is to integrate design and analysis more completely. If you look at the history of computer-aided design and the types of representations that are used, and the history of finite element analysis, and again, the types of representations that were used, these areas just grew up basically independently of each other. But in IGA, you really pull all of this together into one basket. And it's not surprising that there's quite a bit of activity in the computational geometry area now in IGA analysis. So it has different perspectives, but from the analysis perspective, you can think of it again as a generalization of finite elements with the usual refinement schemes, mesh refinement, polynomial refinement, and also an idea of K refinement, where you go to higher order, but you don't retain the low continuity of finite elements, like just continuous functions. You go to smooth functions. So you can increase smoothness with order. So quick tutorial for B-splines and NURBS. B-splines are the, I'd say, most basic tool that's widely utilized in computational geometry and design. And you can generate B-spline basis functions using the Cox-de Boer recursion relationship. And to do that, the first pass, you start with piecewise constants on what you might call a mesh here. And the points in the mesh here are referred to as knots. So this is a uniform knot vector defining these points. And you generate this sequence. And then you can recursively go to first order to get piecewise linears. And these look like the hat functions of finite element analysis. They're exactly that, in fact, and so on. But when you go to second order, you go to functions that do not appear classically in finite element analysis. You would get quadratic functions that now are smooth. They're C1 continuous. And you notice the continuity is increasing from discontinuous C-1 to continuous C0 to C1. And if you go to cubics, they will be C2 continuous, and so on. And you also note that these functions, unlike the quadratic functions of finite element analysis, like Lagrange polynomials, are pointwise positive. So all these functions are always positive. And that has great benefits in design, in particular. So if you take a patch, say from 0 to 5 in one dimension, and you have multiplicity p plus 1 at each end of the knots, you can create interpolatory bases at that point. And this is a non-uniform knot vector because internally we've repeated a knot, as you can see here, and the repetition of knots decreases the continuity. The basic C1 smooth quadratic polynomial basis function, B-spline, is here and here. And by repeating here, we've reduced it to C0 continuous. If you repeat it once more, it'll uncouple the patches. So you can control smoothness and continuity to any degree. So the way you create a geometrical object with B-splines is you take each basis function and multiply it, in this case, by points in the plane. These are control points, okay? They are the amplitudes of these basis functions. And you can see they don't interpolate except for special points. This point, this point, this point. The endpoints and this point are the images of those knots. And if you move a control point, everything will deform smoothly and monotonely. Whereas with Lagrange polynomials, if you move certain basis functions that are higher order, you'll introduce oscillations. Now, this is called the control mesh, and there's another mesh. The first thing you have to learn in computational geometry is that the nodal model of finite elements is a degenerate case. It's the case where the two meshes, the control mesh and what we call the Bezier mesh, become the same thing. There is an extraction procedure where you can take this object in terms of these global basis functions and decompose it into local basis functions, typically Bernstein basis functions, on elements. And you would process these elements after extraction exactly as you process finite elements in a finite element code. So you can implement these ideas in finite element codes rather straightforwardly. Now, the geometry, the object is exactly the same, but you have these two mesh-like representations. If you want a finer discretization for analysis, you just introduce more knots. Okay? So by introducing more knots, what you've done is subdivided your Bezier elements, so you have more accurate basis, and you can see that the control points in this process of refinement are approaching the geometric object. In fact, they converge at order h squared to the Greville, so-called Greville abscisses, special points in the object. You'll also notice that in refinement, the geometry doesn't change. Here, refinement is embedded in your geometry. So if you start off with the CAD geometry and it's exact, you will have it throughout the refinement process. And you can go further, and so on. And you can do it non-uniformly any way you like. Now, the main tool in engineering design is non-uniform rational B-splines. NURBS, so-called, are the most commonly used computer-aided geometric design technology in engineering. And the reason for that is with NURBS, you take a ratio of B-splines and you can create explicit formulas for all conic sections, circles, ellipses, things of this nature, which you need, obviously, in engineering. And here's a construction, a simple construction taking 4 quadratic polynomials and doing a projection by way of a ratio of splines, and you will get an exact circle. Not an approximate circle like in finite element analysis, but an exact circle. You get any conic section. And so you can use this to construct various geometrical objects like surfaces, like a toroidal surface, a product of circles. So this is a mesh of 16 quadratic NURBS, but these are exact circles. And you can refine it in the same way as I said before, right in the object, never changing the geometry. Unlike finite elements where you have to search for the geometry, and it's always an approximation. And you can do this in 3D with volumetric representation, and this is the control mesh here, and this is the Bezier mesh. So you have to get used to the fact there are 2 meshes, and that's different from classical nodal finite element analysis. So the mathematics of IGA is a subfield in itself. The 3 main areas are functional analysis, spectral analysis, and Kolmogorov n-widths. And we've developed work in all these 3 areas. I would say functional analysis goes more or less the way it does in finite element analysis. Kolmogorov n-width gives you the ability to compare different discretizations with the same number of degrees of freedom. And we were able to show very clearly that in many cases, spline-based analyses are optimal and superior to other discretizations. I'll talk a little bit about spectral analysis because you don't really need a mathematical background to understand it. If you're in mechanical engineering, you know about frequencies and mode shapes and vibrations, and that's the essence of spectral analysis. So we'll look at a simple problem, the eigenvalue problem, just for the second order operator, formulated in the traditional way as a Galerkin method. And we'll look at some results. And the spectrum consists of the errors. This is an error spectrum. Eigenvalue errors in red. Eigenfunction errors in blue. And eigenfunction errors in the energy norm, the H1 semi-norm in black, which is the sum of these 2. Now, this result holds for every mode in your system. So if you have 1,000 degrees of freedom, your 600th mode, the errors are right here. The 800th would be right here. So you get what you expect. You get accuracy in the low modes. You get deterioration in the high modes. So you would expect, perhaps, for C0 continuous finite elements, the same thing. These are C1 continuous B-splines. So these are those smooth B-splines. So over here, what do we get? Ooh, we get a picture that's quite a bit different. This branch up here, so-called optical branch, is very much worse than over here. And you get this very bizarre behavior in the middle, big spike in the eigenfunction error, which causes this to happen. So we didn't really know things like this occurred until we investigated this with the hope of understanding the accuracy of the splines. And what we found out is things much more interesting about finite elements. Now, focus on this picture. If we go to C2 continuous cubic splines, you can see the curves here are getting better. They're pushing out to the right. See this? Pushing out to the right. So things are getting better. You're getting better accuracy for more modes. You do the same thing over here, going to C0 continuous finite elements, traditional Lagrange polynomials. The this optical branch is now going off scale, and you get another spike over here. So you're getting errors in the modes that are indicating that there's absolutely no approximability out here. These things are not converging. In fact, what you find is they diverge with P. You can mathematically show the optical branch out here diverges with P. In other words, it gets worse and worse and worse as you increase polynomial order. And if you continue once more to go to C3 continuous quartic splines, this picture is again getting better, more and more good modes. Over here, more and more bad ones. You don't even see the black curve because not only would it be off the picture here, but it'd be even off the slide. So if you've ever wondered why high order finite element methods are not used for things like hyperbolic problems, this picture gives you the answer. Because when you have hyperbolic problems, you're going to have high modal phenomena. You might have a problem like crash dynamics, blast. Anything that goes in there is going to propagate. And you're going to be arousing these modes. And this is why people go back to linear elements. Why linear elements? There's no optical branch. The accuracy is low, but the stability is much better. The interesting thing over here, as you go to higher order, your robustness increases rather than decreases, as it does with C0 continuous finite elements. So that kind of gives some insight. Now, for elliptic boundary value problems, these modes are suppressed by the best approximation property. If you do a spectral analysis, you see the high modes are killed off. Okay, so you live down here, suppressing all of this. This is still a more efficient representation, as you can see. But so for elliptic boundary value problems, you're okay. For hyperbolic, you're not okay. So modeling paradigms. Boundary fitted modeling. That's the gold standard. Let's take a quick look at that. Here's just like simple geometry, hemispherical shell, ring stiffener, exact geometry. You can build an URBS-based discretization, which is the exact geometry. This is solid modeling here. How do you get that reentrant corner when you have just smooth mapping of one patch? You repeat knots, so you reduce continuity to C0 there. And so it's an exact model. It's not typical of practice in industry. And when you compute, because of the smoothness of the basis functions, you don't have to filter the stresses. They're smooth and nice to start. You can, to some extent, you can build these exact models for as-built structures. This is the aluminum testbed cylinder from NASA. It's ring-stiffened cylinder. This is a picture of the frame with the skin, the main rib. This is a section of the main rib. And this is the coarsest mesh. And you need finer meshes for analysis. This is just to get the geometry. Every fillet is there, though, you can see. What do? You refine in place. You haven't changed the geometry. And this is just a few of the primary modes and comparison, a one-shot comparison with experiment. And you can see the comparison is quite favorable. If the experimental work was more accurate, it would be perfect. Okay, that's an analyst speaking. Okay, but back to reality. You can't build exact boundary fitted models of this. You can in principle, but it takes an infinite amount of work. So it has to really be an important application. So the other modeling paradigm is TRIM and immerse modeling. And in finite elements, the history of this was, well, low accuracy method, things deteriorated at the boundary. And then along came Ernst Frank and Alexander Duster, who showed through the finite cell method that if you got the integrals right on the cut elements, you would retain full accuracy. So the way this works is you take a CAD file. This is just an example. This is a single watertight T-spline. Okay, so this is not like traditional CAD. This is a watertight, pristine T-spline. You can see it's a wheel. You drop it into a box. So this is the surface. So this is a box of three-dimensional B-splines. You strip away all the elements that do not intersect the object. You do some mesh refinement. This is the quadrature mesh. I'll say more about that. And then you can basically automatically analyze that way without worrying about building a finite element model. You essentially, from the CAD geometry, you go directly to the finite element model. So let me show you that you can get the accuracy at the interfaces. This is the classic problem of internally pressurized cylinder and elasticity. This is how you might want to model it with a boundary fitted model. These are quadratic NURBs. This is an overkill mesh. It's done with NURBs. So these really are circles, exact circles. And with an immersed method, what you do is you drop your object in, and in the interior, you have material, 1. And in the exterior, the light gray region, you have no material. So that's phase 0 and phase 1. Then you might do some mesh refinement. I'll say a little bit more about this in a second. But this mesh refinement is done with truncated hierarchical B-splines. You have all of these seemingly hanging nodes. Right through those hanging nodes, everything is C1 continuous still. These are quadratic splines. So you can maintain the continuity where you have all sorts of hanging node type structure. And this is technology that was developed by these people some years ago. Very powerful. It's widely used nowadays. Now the key thing is to integrate the cut elements. So the cut elements here, as you can see, this little 3x3 area is this here. Your basis functions are defined on the gray mesh. The blue mesh is just a quadtree mesh to locate quadrature points near the interface so you're accurately integrating the cut elements. And that's the finite cell version of the immersed method. So you do get a densification of quadrature points there. That enables you to get an accurate integral over, say, this cut element. So you can see there's quite a lot of points. There's 4 points per element, but there's also 4 points per quadrature element as you refine. One thing that's important is the geometric accuracy of the trim boundary. It's critical. Where does that come from in a real application? It comes from CAD, some kind of an input file. So not only is it accurate, it's in the sense of CAD, it's exact. Okay. And pictorially, you can see the accuracy is the same for immersed or boundary fitted. If you take the immersed solution, take cuts, different angles here, this is just the hoop stress. This is the exact result, and all the results lie exactly on top of it, including the results of the hoop stress along this curve, which you may be interested in because that's going to be the maximum typically. In this case, it is. And that point is basically exact. So you can get the accuracy. So I'll quickly show some 3D applications, real applications in computational cardiovascular medicine. And this is in collaboration with a company called HeartFlow, in which a coronary CT angiography is done, from which a patient-specific model is built of the coronary arteries. And they detect through the image certain areas where there are lesions, thick plaques that may be vulnerable. And then HeartFlow does a CFD analysis of blood flow in the arteries. And from the CFD analysis, they pass us at the Odin Institute with the traction vectors along the surface. We pick up all the material properties in this box, including the area of interest, by way of the Hounsfield units from the image. And then we do a stress analysis and we look at these vulnerable areas and try to determine just how vulnerable they are. So again, it involves 3D truncated hierarchical B-splines around the area of interest, local refinement at the lumen boundary, as you can see, and accurate octree quadrature. In the medical business, everything is clinical trials. So this was the Emerald trial. And from it, we have over 200 lesions that we studied. Okay. And we created a biomarker that has now given us the highest value of area under the curve, if you know what that is. This guy right here, specificity, sensitivity diagrams. And so we analyzed over 200. We created this biomarker, and we found it was better than the current gold standard upon which HeartFlow's businesses rest. So we have something better. We published our first announcement of this a few weeks ago and filed a provisional patent. This study was fully automated immersed IGA model construction and analysis. Over 200 analyses were built and analyzed without any user intervention. Took in the lumen geometry, the traction vectors, built the models of the exterior, very heterogeneous models, many quadrature points because we're using the finite cell method. We did use GPUs. And essentially went to the beach and came back, and all the results of 200 models were done, including the statistical analysis. And this would have been difficult, if not impossible, without immersed IGA. So both of these technologies, boundary fitted and immersed, are useful. And I think in the future we'll see a synthesis of them. This is sort of an example that we worked on some years ago. And this is a boundary fitted artery model. So this is an artery wall modeled with hyperelastic, nonlinear hyperelastic constitutive equation. The flow domain is a variational multiscale solver for the Navier-Stokes equations. And the flow domain is moving, okay? But the heart valve, the leaflets, are immersed in there. So they are moving and contacting through the background mesh, which is moving and contracting. So this is a synthesis of body fitted and immersed for a particular problem class. So let's go to the future. Obviously, it starts off with a continuation of the present. Computational medicine, as I said, is a big field. Phase fields are everywhere. You've seen examples of binary phase field, TrimCAD, immerse methods. Also, topology optimization can be framed in the context of phase fields, where you have material as 1, where you don't have material as 0. But you have continuous phase fields, for example, fracture and damage. And let me give an example of that. So phase field fracture has become kind of another mini boomlet in the mechanics area, where you have a phase field that represents the fracture pattern. And there are various theories. I won't go into that. But this, you can see, is a dynamic calculation where you're pulling the top and the bottom apart. And it looks like you're fragmenting the structure. But all calculations are done on the original mesh. There's no remeshing or anything like that. So that's the beauty of this technology. Additive manufacturing is also a continuous phase field, also multi-phase flows. The original example, I would say, of a phase field equation with the Navier-Stokes-Korteweg equations. And these are equations that also involve higher derivatives. The Korteweg stresses are third derivative stresses. So it's very convenient to be able to use smooth splines when you do a variational discretization of them. So this is a three-dimensional boiling simulation. So you have water below the blue surface. It's being heated from the bottom. And you have a cooling plate that here is invisible on the top. And the heating on the bottom, these are density profiles. You create plumes of vapor, water vapor on the bottom. So you've changed phase. They come up, they pierce the free surface, they condense on the top, and the droplets form and drop back down. So this is the temperature profile. So you can see the structure of the plumes. And you can see in this image the formation again of droplets. And here's an animation. You can see how fine scale the meshing is down here. Okay, and this is done from fundamental principles, just the Navier-Stokes-Korteweg equations. And again, smooth splines are used there. Okay, so another thing we're seeing now, integration of design, analysis, and manufacturing with IGA type technologies in industry. And of course, machine learning applications in design analysis. That's the elephant in the room of it. I mentioned HeartFlow. The way HeartFlow works as a sort of an analysis company is to segment the image to determine the lumen boundaries and the boundary of the outer wall of the coronary arteries. They use deep learning. And they've been doing this for years and years. So they were an AI company before they realized they were an AI company. They thought they were a software company. But now since they've gone public, they have proclaimed themselves as an AI company because your stock price goes up by about order of magnitude if you're an AI company over what it would normally be. Nevertheless, to do the analysis to compute the pressure drops and the FFRCT so-called, they use CFD, same code that we developed at Stanford, the same algorithms at least 30 years ago. So what's the reason for that? Can't get the accuracy yet in the CFD with a neural net. So the future. Well, AI, it's everywhere. So we have deep learning applications and finite elements, IGA, computational mechanics. It's presently not competitive for forward problems of solving PDEs. Finite elements, IGA, faster, more accurate if you have to do one-offs. However, the possibilities are there for merging with and improving finite elements and IGA. Better architectures, fast equation solvers, inverse problems are an area where it's very successful. Reduced order surrogate models. And it's already a proven technology for model development in computational medicine, as you saw in the example of HeartFlow. Well, now, of course, we are deeply involved in the era of LLMs and agentic AI. And this creates different reactions in different people. Agents are thrilling some people and scaring the bejeebers out of some others. I want to remind you that we have some experience with this going back to 1968. I don't know if you know this movie, but Dave is saying, open the pod bay doors, Hal. Hal is the supercomputer AI. And Hal is running the show in the space vehicle. And he's not responding to Dave. So Dave tries again. Open the pod bay doors, Hal. No response. And then, Hal, I'm sorry, Dave. I just can't do that. So we have to be careful with agentic AI, as I think people have already realized. But it's exciting technology. So the future, predictions. I don't know, so many young people now, they maybe don't know who Yogi Berra is. I won't mention what his primary career was, but he was a great philosopher. And his philosophy, one of the things he says, it's tough to make predictions, especially about the future. So I think those are words of caution. And they become very prescient when you see some of the remarks made by some famous smart people, like Lord Kelvin, who said in 1883, X-rays will prove to be a hoax. And he didn't learn his lesson when he said that. He said in 1895, heavier than air flying machines are impossible. And then Albert Einstein came along later on. We know he's a smart guy, but he said there's not the slightest indication that nuclear energy will ever be obtainable. The best of all, though, is William Stewart. He was the Surgeon General of the United States in the 1960s, and he proclaimed in 1969 that we can close the book on infectious diseases. You remember that? We opened the book, and thank goodness it's over. Looking forward to the future. Thank you.
Thank you very much for the wonderful presentation. I want to ask your thoughts about this very popular field the last 5-10 years of scientific machine learning. You mentioned a few things about deep learning, right? But we have all this enormous work of PINs, for example, physics in formula networks, that essentially does everything opposite from FEM, right? No variational formulation, no functional spaces with compact support, no convergence guarantees.
Well, I mean, if let's say you build a neural net, okay, you're building a function or you're building an operator, right? And you are creating basis functions. You may be using ReLU or something else, but you are creating a composition of basis functions. So those functions are there. In fact, if the current issue of SciAm journal, you know, the one that has kind of the reviews in it and all, is analyzing the function spaces themselves as approximation spaces from a mathematical point of view. Say, they're looking in particular at ReLU. So I mean, people kind of understand that. So I wouldn't say that that isn't there. It's just a different way of creating a function, right? I mean, in finite elements, we have these ways of creating multi-dimensional functions, IGA. Very often, they start out with sort of tensor product type things to go to multi-D. But in like ReLU, for example, you're computing, you're taking the composition of functions that are 0 and then ramp. Okay, you do that, you're going to get linear approximations on polygons. You know, that's your function space. And then you can build an operator by...
So you see the two worlds basically as very similar or very different?
I think it's a different paradigm of function construction. Just like IGA is a different paradigm than classical finite element analysis. But the thing in ReLU, it is structured differently. You build your multi-dimensional discretization with composition of one-dimensional functions.
And what about the variational formulation that is completely missing?
That is not necessarily part of that. I mean, these are data-driven techniques, so how you generate that function is from data. That data could be coming from the solutions of variational problems, for example. Then it would be implicit in some sense.
I'm talking for the case where they're using pins in the context of solving PDEs, not necessarily of incorporating data, right? Where they completely abandon the variational formulation and it's only about minimization of
well, okay, but you're minimizing a functional, right? You're an optimization guy, you know this. Yeah. You're minimizing a functional. All right, so what is the functional? Pins is relied on least squares type functionals. My criticism would be, let me minimize that functional. Let me minimize it with any functions I want to minimize. What do I find out? I get lousy results, okay? That's the weakness of pins. The function minimization problem is not the right problem. If you work with a variational formulation and you take residuals of it and you minimize a potential coming from those, your network is doing the finite element method.
Okay, got it.
My contention is neural nets will, when they get really good at this, they will have discovered the finite element method.
That's what I want to hear.
Okay.
Any other questions?
Thank you for your talk. Really quickly, could you speak to like maybe the computational time it takes to perform? Could you speak to the computational time it takes to perform an FEA with, let's say, n number of elements versus an IGA with maybe a similar accuracy?
Well,
like what is the...
okay, we have to, similar accuracy. Well, then I think IGA wins.
Like
because
order of magnitude, do you have like a time, I guess? Like what's the...
I mean,
okay.
All possibilities, right? You have to take an example, then you can say what it is. But the accuracy per degree of freedom in IGA with optimally smooth basis functions is higher and it's with C0 finite elements. So on that level, you can win the battle. You will have a smaller system for if you equivalence on accuracy, okay? And that's seen all the time. On the other hand, if you're doing something like I was showing you with the brute force approaches we would do to quadrature at the cut cells, you're going to engender a lot of quadrature points. That's not a good idea. In computational geometry, there are methods for doing things like that are really fast. And so you want to use that. I mean, we're in the research business, so we just kind of do whatever is easiest, I guess, to demonstrate. But I think you should be able to win the battle because basically you have a more robust, accurate, underlying technology. And when people do comparisons, they find you win the battle. I don't think I've ever seen a case where people say, oh, look, finite elements are much better than IGA. Have you? Not yet, okay. We're 20 years down the pike, so one of these days.
So, can I ask a question?
No.
So, there is the effort going on, enormous effort, as you showed in if you have a given physics, you can more faithfully, reproduce whatever that physics predicts. What about additional new physics coming in, for example? You showed these very nice boiling simulations of the Navier-Stokes Korteweg. You got these gradients and surface energies, fracture, and now you couple it with diffusion of things. Where do you see things happening in mechanics generally?
Well, I think multi-physics problems there's a lot of activity in that area. There's even a lot of commercial activity in that area. That's going to continue. And I think finite elements and IGA are the ideal technology for that because you express everything in a coherent variational statement with all the coupling and go to town, I mean, I don't know what you want me to say.
I don't.
I know you wrote a book on the topic. It's very nice. You should ask him. He even wants to do problems where he doesn't even know the physics, right? Yeah. But he wants to get the right answer.
Get the pins.
No, he's not going to use pins. He's going to use something else.
Anyone else?
Pins and needles. Use needles,
Yes, sir.
Can you expand a little bit on the patent that you were talking about with regards to the cardiovascular flow in the coronary arteries?
What did you, what?
Yourself and what your background is, his background, could you identify?
My name's Jeff Raines, and I'm a long time ago graduate of HST, which is our...
Very, very nice, thank you.
Okay. And when you said...
And the question is, you showed some images that you had put up from computational aspects actually they were the coronary arteries
Exactly.
at the aortic root. And you said that there were some new patents that you had just put in. I looked at the date. It was like last month.
Well, this, I think we filed the patent application March 26th, something like that, provisional.
That's what I
Yeah.
saw.
The problem in coronary artery disease is what's referred to as vulnerable plaques. And these are atherosclerotic lesions, typically that are soft. Could even be a lipid pool, maybe have a little bit of calcium in it, but they're very, very soft. And if they're soft and thick, the lesion, the emboli there, are separated from the blood flow by a thin fibrous cap. And that cap is typically inflamed. It's under a high state of shear stress. And because of the soft...
And it has soft shoulders, which are really the
right.
real issue.
And if you think of it in the sense of like a cross-section cut, you've got a thin cap that's, and the big force is the pressure. And you don't have much behind it to carry any of that hoop stress that is generated. So the cap has to carry it. And the cap is very thin, 20 microns to 100 microns. And as a result, under that severe state of stress, these things rupture.
They rupture, and then the thrombotic material goes into the stream.
It goes into the
and
bloodstream
You get a thrombosis.
immediately,
Yeah.
a second or two. And
Yeah.
then you have a heart attack, or if it's a small one, it goes up in the brain, it can be a stroke. Yeah,
Yes,
yeah.
indeed.
So what we tried to do in that work, that whole work is a long story. But what we tried to do was to go from just the fluid dynamics diagnostic, which was basically pressure drops across the lesion, to what really is occurring during the failure of a fibrous cap, and that is it's a problem of structure. It's a structural analysis problem. And so we try to estimate the stress in the actual lesions and combine that with a couple of other things into a biomarker, and that biomarker then exceeded the FFR.
Well, the biomarker is extraordinarily important because what we don't know, you can have somebody that has atherosclerotic plaque, but if they don't have vulnerable plaque, they're not susceptible to disease.
That's right, yeah.
And to separate them is almost impossible.
Well, but we did a pretty good job.
That's why I asked the
That's why we're patenting it, yeah.
All right. So this is great. Thank you, Tom.